All right, we have a few more things that hopefully help us describe some of the situations we're running into here with the different types of zeros we can get. We've got some rational values that we can get. We've talked about real zeros and so on. We can actually find a shortcut to figure out what kind of combinations for types of numbers we can get as well for our zeros. So one of those things that helps us out is called Descartes' rule of signs. And definition wise, what it's going to tell us is this. It's going to say that if I take my polynomial and count the number of sign changes, it's going to give me the number of positive real zeros. Now, whatever that number of sign changes is, I can subtract an even integer from that each time to find every possible situation. So if I ended up with 7 sign changes, I would subtract 2, I would subtract 4, I would subtract 6, and that's going to tell me that I'm going to have either 7 positive, 5 positive, 3 positive, or 1 positive real zero. To find the negative real zeros, same situation, except I'm going to substitute everywhere there's an x in my polynomial with the opposite of x, simplify that, and then do that rule all over again. And that's going to tell me how many possible negative zeros there's going to be. So easiest way to do this one is let's just take a look at this situation. So if this is our polynomial, we have 3x to the third minus 5x squared minus 6x plus 4. Alright, so if there's my polynomial, so let's take a look at this one first for f of x. This is going to give us our possibility for positive sign changes. So we're just going to look at this in terms of signs. So here's a positive, here's a negative, here's a negative, here's a positive. So we just count how many times the signs change. So in this case, there's 1. This one doesn't change from here to here, but from here to here it goes from negative to back to positive. So this one, there's 2 sign changes. So let's take a look at what happens with f of negative x, and we'll come back to this in a second. So f of negative x just means everywhere there was an x, we're going to substitute in a negative x. Oops, getting a little sloppy again with that. And then we're going to simplify this before we do our count like we did up here. So here, a third power with a negative is going to keep it negative times positive, gives me negative 3 x to the third. Here a negative squared is going to become positive times this negative. Well, positive times negative is negative, so negative 5x squared. Here negative times negative is positive, so positive 6x plus 4. So here's our simplified form. So now let's check our signs. Got a negative, negative, positive, positive. So from here to here, negative to negative doesn't change. Negative to positive, there's our first sign change. And positive to positive doesn't change again. So we have only one sign change. So what this is going to do is, let's go back to our positive one up here. Since we counted 2, we know that there can be 2 positives, but because we subtract an even integer every time, the first even integer would be 2, so if I did 2 minus 2, I get 0. So that tells me for positives, I'm either going to get 2 positive zeros or I won't get any positive zeros. Now the same situation down here with the negative, we only had one sign change. So if I followed my rule again for subtracting an even integer, well, 1 minus 2 would be negative 1. Well, since this is a count, I can't have a negative 1 amount of something. So that would be my only choice. So I could only possibly have one negative value. Now we combine these two things because there's some combinations here that we have to deal with. So usually what I'll do is I'll make a chart like this. It'll say my positive zeros, my negative zeros, I'm going to throw in imaginary zeros because we still have to have a total of 3 every time, and then I'll put a total at the bottom. So I'll set up my chart this way, and then I can use this to find any combinations that I get. So one combination that I got was 2 positive with 1 negative. But I also had to look at this combination, 0 positive with 1 negative. So that part's pretty simple. Now again, because of one of the theorems we were talking about in another video, one thing that we did say was whatever our exponent is, we have to have that many zeros. So I know I have to end up with 3 zeros each time. Well, if this is the situation that happens, I've already got 3 used up, so I know none of them will be imaginary. This one, I've only used 1 of my 3 up, and this has to be a 0 because that was my other combination, so I got 2 left over there. So I'm either going to get this situation or I'm going to get this situation. So I'm either going to get 2 positive, 1 negative, and no imaginary, or I'm going to get 1 negative and 2 imaginary. So again, if I do a third power and do my graph, it's either going to cross 2 times to the right of 0 and once to the left, or it's going to cross once to the left and have 2 other turns, but they're not going to cross the x-axis. So that's what Descartes' rule says. Now we also have one other one that we can use to kind of shorten things up a little bit, and that's going to help us find upper and lower bounds. So upper and lower bounds. All upper and lower bounds is doing is this. If you remember back when we found our values for the PQ, our possible rational roots, we're going to be able to take that whole list of those that went all the way from here to here, the smallest to the biggest, and we're going to find a spot that's going to be an upper bound and another spot that's going to be a lower bound that's going to say, all right, out of that whole list of all the possible ones, the only ones that are actually going to exist are going to be in this interval. So if we did have one of the problems in one of the earlier videos, we had 32 possible rational roots. Well, if any of those were bigger than whatever we find our upper bound to be, we don't even have to check those. They're not going to exist. If any of them were smaller than what we find our lower bound to be, we don't have to check those. They're also not going to exist. Now, here's what the rules are for our upper and lower bounds. We're going to set up a synthetic division where we're going to get some values in here, bring this down like normal, still going to have our remainder, and of course we're going to put some value out here. We're just going to call this C for the time being. So what's going to happen is 2 things. We're going to check one for upper bounds and one for lower bounds. So of course we're going to do this, multiply, get that number here, add them up, bring something down here. Multiply, get that answer here, add them up, bring that here. Multiply, get that answer here, add them, get that there. So we're going to do this and look for a pattern. And the pattern we're going to look for is going to be what happens down here, only in our last line. Now, in that last line, if every one of these things on the bottom turns out to be positive or 0, then that means that we just found an upper bound. Now, if those things alternate, and alternate in terms of signs, that means we found a lower bound. So if it goes positive, then negative, then positive, then negative, and so on, it's a lower bound. If you get 0 in one of these bottom rows, 0 is going to be positive or negative, whichever we need it to be to keep the pattern going. So that's how we're going to do our positives and negatives. Now, those are the two situations, upper bound, lower bound. What we pick to put out here for C, if we put a positive C, we're going to be trying to find our upper bound. A negative C is helping us hopefully find our lower bound. And we want to start and work our way out, so we really want to start as close to 0 as possible and work out towards the upper bound and out towards the lower bound. It's conceivable I could just say 10 million and negative 10 million, and I'm probably going to make it and find, yep, that's an upper bound, that's a lower bound. But we want the most restrictive upper bound and most restrictive lower bound. So let's take a look at how this plays out in one of the problems that we've been working on recently here. So let's